All right. Welcome everybody to the session on language design. It's my great pleasure to announce the first talk, which is about DeepSEA, a language for certified system software. And the talk is given by Yuyang from Yale University.
Hello. Hello everyone. My name is Yuyang. Thank you for coming to my talk, DeepSEA, a language for certified system software. Sorry. Formal verification is the surest way to develop a secure, trustworthy software. We need a stable operating system, trustworthy compiler, verified network stack, and we also want to verify blockchain, self-driving car, etc. But developing and verifying such large systems are very hard, requires a lot of human labors, and I think we do not have good language support. Actually, 45 years ago, Tony Hoare has already proposed that we need such a good programming language that gives assistance in expressing not only how the program to run, but what is intended to accomplish. And it should enable this to be expressed at various levels, from the overall strategy to the details of coding and the data representation. What such a good programming language should look like? We are in favor of implementation. We wanted to generate efficient code, focus on low-level control, and relies on minimum runtime support. Such good examples are C and assembly, but they are not suitable for writing specification. A good specification language should be high-level enough, guarantees memory safety, pure, and support equational reasoning. Such good examples are COG, Isabelle HOL, and in addition, to build a large system, we prefer modularization, encapsulate internal effect, and be object-oriented. Such examples are, there's a lot of successful programming language out there. But is there a single language that supports all these features? I'm talking about a universal language, a language that supports all language features and interaction between them. Well, as far as I know, I cannot find such a language. But do we really need it to build a large verified system? I think the answer is still no. The key is certified abstraction layer. Each abstraction layer only requires a small amount of features. So we just need a language that can grow with certified abstraction layers. And we can build more functionality, provide more high-level features on top of some low-level features. Based on this idea, we started the DeepSEA project, a project that develops programming language which can grow with certified abstraction layers. This paper presents our first step towards this direction. We designed the first language that supports equational reasoning, abstraction refinement, layered specification, effect encapsulation, and composition. They are enough to grow itself by adding more language features in different abstraction layers. For each abstraction layer, we developed a verified compiler that generates efficient C implementation, COG specification, and the proof relating them. Then we use certified abstraction layer library to link them into a large verified system. We also developed and verified two softwares, a hash function, SHA-256, and an OS memory management module. Our ultimate goal is to prove a refinement between a high-level specification, the yellow box, and a complex implementation, the green box. But such proof is usually very hard, especially when a green box becomes big and complicated. So instead, we divide the implementation into many layers, add a small part of implementation in each layer, prove refinement for it, then compose all layers together. This can significantly reduce the proof complexity. Take our memory management example. You do not have to read it very carefully. I'm just showing the overall structure of a typical DeepSEA source code. Here, user firstly decompose her system into many conceptual layers, then write down DeepSEA code to define what each layer looks like and how they are composed together. Each layer may have one or multiple objects. DeepSEA uses layer signature to describe this object's interface, as you can see on the right corner. and uses layer declaration to define which object instance should be included into this layer. So our memory container layer includes one single object or container input, and our MAL MAL layer has one single object called PMM. Then each object has its own signature. It may rely on other objects, have its own private variable, and expose some functions that work on its variables or dependent objects. And here I will show you how each object gets decomposed into many small parts and be verified. Here, user write down DeepSEA source code. It will be desugared into a COG specification, a C implementation, and a COG proof relating them. The implementation will later be compiled into assembly function by a verified compiler COMSAT X, and later it can be executable with the help of pretty printer and assembler. I will use this simple example to show you how this 4-box looks like and how they are linked together. This is a simple function defined inside a DeepSEA object. This object has a private variable, an integer array, A, and this function takes an index n, firstly check if it stays in bound. If so, it initializes the first n elements of array into 0. Has generated the C implementation. It's not intended for human beings to understand, so let's just skip that. You just only need to notice that this assertion line disappeared in the implementation because it only serves to help people to reasoning at the specification level. If we can prove that this assertion never fails in specification, then we can safely delete it from implementation. Now let's focus on specification. We want to encode our specification in proof assistant language COG. It should work on abstract data, trigger failure when a searching condition is not met, and allow modification on abstract state. So in the end, we use a simple option monad to encode its behavior. Every specification map a starting state into a wrapped pair. If the specification failed, it should just return none. Otherwise, it should return an ending state and the computation result of the specification. Now we can use the COG function as a specification. It converts assertion into guard operation, converts assignment into modify operation. And there's this for-m loop. It's just a recursively defined COG function. One thing to notice here is this Z-map. It's a COG module that describes infinite map from index to data. And the data type of this argument, n, is unbounded integer. So reasoning with this kind of specification is much easier than reasoning directly on C. You no longer need to worry about integer overflow, array accessing out of bound, etc. But you can only do this after proving a refinement between specification and implementation. A refinement just wants to say that the specification captures the full behavior of implementation. In other words, the specification's all possible behaviors forms a superset of implementation behaviors. We usually use backward simulation to describe this, but it's hard to prove. However, also instead, DeepSEA only proves forward simulation. Then we rely on this fact that every step described in DeepSEA language is deterministic, so we can deduce backward simulation from forward simulation. You can find more discussion on this topic from COMSAT paper. The forward simulation states this fact: starting from a memory state M and an abstract state S, and they are related by some matching relation R generated automatically by DeepSEA. If executing the specification converts abstract state S into S prime, then the corresponding implementation should modify the memory state from M to M prime, and the ending states are still related by the same matching relation R. You might ask, what exactly is this R? It's just a conjunction of some data type refinement relations. So each DeepSEA object has some private variables. The DeepSEA compiler will automatically generate a concrete data type and abstract data type for it. These R just establish a linking between these two data types. For instance, a DeepSEA Boolean data type should hold a relation that links a coq value true with C value 1, a coq value false with C value 0. As for integer, it simply relates n with n, plus an extra requirement that this number must be between 0 and 2 to the 32. As for array, it requires that every element within an array satisfy this matching relation. Once we have this matching relation defined, let's look at how to preserve it during execution. We rely on the following observation. The program only interacts with its state or abstract or memory by reading and writing data. So we just need to prove these two properties for every variable. Setter property, storing a valid value preserves refinement relation, and the getter property, retrieving value from matched state returns valid value. Now one thing still remains unproved. How to guarantee that only valid value can be stored? Well, we call it a verification condition. At every possible execution point, only valid value can be stored into valid place. The compiler generates verification condition for every function. Let's look at our simple example again. Its verification condition states that for any state that satisfies our precondition, no matter how many times we execute the looping body, the ending state still satisfies that the index I stays in bound and the value to be stored into array does not go overflow. We developed an Ltac library to automatically prove verification condition. It works by introducing effect of execution into proof context, destruct invariants, use some coq tactics like omega and auto to solve everything else. It works well in our case study, and we are gradually reinforcing it. Now we have finished the refinement proof for every function. We can collect their specification to form an interface, and we call it abstraction layer. It encapsulates low-level details, but also captures the full behavior of its implementation. So we can later build more functionality on top of this abstraction layer. It serves like an API. We use it by doing function call from high level to low level. Its specification is just the unfolding function body at the calling point. As for implementation, the layer library will find the correct C function for us. Until now, you might notice that the smallest construction unit is object. Objects group together into layer. Layers are piled up into the final system. To help user construct their system, we provide some layer composition operations. Two objects built on top of the same layer can be merged into one single layer. We call it a vertical composition. We also support a horizontal composition, allowing you to pile up a lot of layers. And we also allow user to define a new layer without adding any new implementation. We call it a pure refinement. It's useful when you need a more abstract interface. For example, DeepSEA can help user to lift a C array into an infinite map, but our user might want to reason with association list. So Shim can manually define another layer, provide a data type refinement relation between association list with the map, then manually prove the simulation relation. Those are all the technical details I want to share with you. They are implemented with 10,000 lines of OCaml code and 18,000 lines of coq code, in which we spent 2,000 lines to develop a verification condition Ltac library, 3,500 lines of code to define data type refinement relation, and the refinement proof relies on 7,000 lines of refinement lemmas. After that, we spent 4,000 lines to construct layers and make them compatible with layer library. Then we can prove two case studies to show DeepSEA's power. The first example is inspired by part of VST project. 5 years ago, Andrew Appel verified that this hash function by writing down 169 lines of coq specification and 8,000 lines of refinement proof. But with DeepSEA's help, we firstly write down 400 lines of specification, use our compiler to generate a C implementation. It has almost the same performance comparing to VST's implementation. Then we did a manual pure refinement proof from our specification to the VST specification. That took about 600 lines of code. If we only compare SHA-256 core function, block data order, VST's work costs 1,788 lines of code, and this figure has been reduced to 952 lines in recent years, but DeepSEA only requires 308 lines of code. Another example is rewriting 30-cores memory management module with DeepSEA. 30-cores was developed entirely by manual proof. This module took 8,000 lines of code, while with the help of DeepSEA, we only wrote 1,000 lines, including DeepSEA specification and a pure refinement proof. I think now is a good point to recap Tony Hall's quote. And we are confident to say that DeepSEA programming language gives assistance in expressing not only how the program is to run, but what it is intended to accomplish. And it enables this to be expressed at various levels, from the overall strategy to the details of coding and the data representation. We accomplished this by supporting equational reasoning, abstraction refinement, layered specification, effect encapsulation, and composition. DeepSEA source code are constructed into multiple abstraction layers. For each layer, the DeepSEA compiler generates efficient C implementation, a Coq specification, and a proof relating them. The key idea behind this is enabling this language to grow with abstraction layers. That's all of my talk. Thank you.
Thank you. Hi, I'm Gervon Le Guernic. Thanks for your talk. Do you have some, your proofs, you do them in Coq. And so I was wondering, do you have some feedback that is provided back at the DeepSEA level? Or the user asks to, if there's a mistake in the proofs or whatever, he can't make his modification at the DeepSEA level. He has to understand what's going on at the Coq level.
Yes, we have two kind of type checks. Firstly is this OCaml compiler will do the first type check. If you have some syntax error and some inconsistent definitions, it will just report at that point. Then we generate a bunch of Coq code and we run Coq compiler on them. If something went wrong, the Coq compiler will tell you what went wrong. And in addition, our generated specification written in Coq is very similar to the original DeepSEA source code. So the error will report report on this deep specification. So I think a user can easily understand what part their code went wrong.
Okay, thanks.
Thank you.
Hi, thanks. Can you please go back to the Tony Hoare quote? It talks about giving assistance, which you say your language does, but to me, I read that as a statement about the users of the language. And so I'm wondering whether anybody other than the designers of the language used it, and whether, if so, you found that it actually helped them.
So do you mean this talks about develop a language?
Well, this says it should help give assistance, presumably, to the programmers who are going to be using the language.
So
right. I'm wondering whether you tried to assess whether it actually assisted the users of the language, or if you mostly just used it yourselves.
We currently only developed 2 case studies by ourselves, but I think it's very easier for user to understand. They only need to write down DeepSEA source code, and they do not need to interact with the underlying Coq generated Coq code.
So this is more of a goal then than something you've already evaluated?
Kind of.
Okay, thank you.
Thank you.
Hello, Mark Feely. I noticed that you mapped the int type to non-negative integers. Is that a limitation of your system? Does it simplify things?
You mean this integer type?
Yes.
The integer type in DeepSEA data type is just unsigned integer. We make it look like this. And of course, you can support some signed integer by adding some other data type. It's very easy to add a data type into as a plugin into DeepSEA compiler.
Okay.
Yes.
Thank
And
you.
we did this because we want to firstly verify operating system where you do not need a signed integer in it.
Okay, thank you.
Thank you.
One last question.
Hi, thank you for the talk. I was curious about if you could say a little bit more about the translation or the proof besides the equivalence of the DeepSEA program and the generated C. I mean, so for instance, like how restrictive is that subset of C that you're operating with? And I mean, like what, like, did you as part of this project, did you develop like a model of your own model of C's semantics, or could you talk a little bit more about that?
Oh, we use CompSert C semantic.
Okay.
I think
All right.
that explains all.
Thank you.
Thank you.
All right, let's thank the speaker again.